This lecture is part 1 of section 4.3 from Math 311, a course on linear algebra from Western Illinois University. And the topic is eigenvalues and eigenvectors of n by n matrices. So in this section, we're basically going to be generalizing what we did with 2 by 2 matrices. And you'll see that there's going to be a lot of common ground, and we're just going to be extending them. The ideas of characteristic polynomials and determinants and eigenspaces. So let's go through the theory first. So if A is an n by n matrix, and lambda, for now, we're going to assume it's just a real number, we say lambda is an eigenvalue of A if and only if AB equals lambda V for some non-zero vector V. Okay, and then that's the definition of an eigenvalue. And then this, of course, implies that AB minus lambda V is 0, and we can factor out a V, and we get the matrix A minus lambda IN times V is 0 for some non-zero V. And because V is non-zero, that means the null space of this new matrix, A minus lambda IN, is not 0. And from the theorem on invertible matrices, it means it's not invertible, and that is equivalent to saying that its determinant is 0. Okay, so we're looking for numbers lambda which make this the determinant of this matrix 0. Now, if we remember the way we calculate the determinants, if we just like in the 2 by 2 case, the determinant is going to be an expression in lambda. Okay, as we'll see in our examples. Okay, in fact, it's going to be a polynomial on lambda, and by that I mean that if we were to just let lambda be an indeterminate, or if we were to replace lambda with x without giving any numerical value for x, we get a polynomial x, and that's the characteristic polynomial. Okay, we could write this as just x, a determinant of a minus x in, where x is a variable, but usually we just stick with lambda since that's really the only variable we need. Okay, and so the roots of this characteristic polynomial will be our eigenvalues, so which is what we have here, and then the eigenspace of lambda. Remember, the eigenspace is all the vectors v such that AV equals lambda v. That's going to be equal to the null space of this matrix A minus lambda IN. And that the way we do that is there are too many vectors in the eigenspace to write them all down, so we'll be finding a basis. A couple other things before we go into the examples. We have this idea of algebraic multiplicity and geometric multiplicity of eigenvalues. And we're going to just define what they are. The algebraic multiplicity of lambda is just the multiplicity of lambda as a root of a characteristic polynomial. Now, what do we mean? Remember what that means. When we learned in characteristic multiplicities of roots, we're talking about how many times the factor x minus lambda appears in the factorization of the polynomial. So remember, like if for example, if f of x is a polynomial and f of 3 equals 0, let's say, that we know that x minus 3 has to divide f of x. X minus 3 is a factor of f of x. Okay, and so x minus 3 times some other polynomial g of x is equal to f of x. Okay, but x minus 3 might appear several times. So if if this is, maybe we can write x minus 3 to the k times g of x times f of x. And then as long as it's g of x, g3 is not a root of this g of x, then x minus 3 doesn't divide this polynomial. So we would say the algebraic multiplicity of 3 is k, whatever this number k is. Okay, so that's the algebraic multiplicity. And to do that, we need to look at the characteristic polynomial, of course. The geometric multiplicity is the dimension of the null space of A minus lambda IN. Okay, so that's just the dimension of this null space. And we're going to see that the geometric multiplicity is always going to be less than or equal to the algebraic multiplicity. Sometimes they'll be equal, sometimes they won't be. But we'll see way down the road that's going to be a very nice situation when the algebraic multiplicity and the geometric multiplicity are the same. Okay. All right. So the way we're going to be doing these examples is same way, sort of the same way we did with a 2 by 2 case. Okay, where we're going to first find the characteristic polynomial of A. A, right, and then set it equal to 0, find the roots of a characteristic polynomial of A. Okay, and then for which of course are which are the same thing as finding the eigenvalues. And then for each eigenvalue, find a basis. For each eigenvalue lambda, find a basis for the null space of A minus lambda in. And but this stuff is actually we've done before, because we've already, we know how to find the null space of a matrix, or at least we should. And in fact, these, once we find, because these are these lambda is an eigenvalue, this step might not be as difficult as you think. Okay. The one thing about finding characteristic polynomial, of course, is you're trying to find the determinant of this matrix. A11 minus lambda, A22 minus lambda, so on. Okay, that's A minus lambda in. All right, so that's the way we do these. So we'll be doing, we've already done 2 by 2 matrices, so we're going to start with a 3 by 3 matrix in this first example. So let's first find what A minus lambda I is. In this case is A minus lambda I3, and that will be the matrix 1 minus lambda, 0, 0, 2 minus 0 minus lambda, 1, negative 3, 2, 1 minus lambda. Yeah, and I think because we have 2 zeros in the first row, it makes sense to expand on the first row, and that will be easy. Because this will just be 1 minus lambda times the determinant of this 2 by 2 matrix. Okay, which when we multiply this out, this is 1 minus lambda, 1 minus lambda minus 2. This is 1 minus lambda. This will be lambda squared minus lambda minus 2. And we multiply everything all out. And this actually, you could use a quadratic formula, but we don't have to. This factors nicely as lambda minus 2 and lambda plus 1. Okay. This, by the way, and this, of course, is the same thing as minus lambda minus 1. Okay. All right, so we want this to be equal to 0, and it's very easy now. We can see that the eigenvalues will be set each of these factors equal to 0. We get lambda equals 1, 2, and negative 1. And we can also see that the algebraic multiplicity of each eigenvalue is 1, because that's exactly, that's how many factors. Lambda minus 1 only appears once. So that's why this multiplicity is 1. Algebraic multiplicity of this is 1, and so is this, and so is this. They're all 1. Okay, now let's find the eigenspaces. So for lambda equals 1, actually, let's see. Yeah, we'll do it lambda equals 1 first. So what we're going to do is we're going to plug this lambda equals 1 into here and see what we get. This will be 0, 0, 0. Then this will be 2, minus 1, 1, and 3, 2, 0. Okay, so what we get is 0, 0, 0. 2, minus 1, 1, and negative 3, 2, 0. Okay, so this is a minus lambda I, where lambda is 1. Now, the thing is here, what we're trying to find the null space of this matrix. So we want to find vectors in the form x, y, z, such that this product is 0. Okay. Well, let's look and see what we get. If we multiply this out, we could do reduced row echelon form, but we don't have to do that. This is 0 times something equals 0, so 0 equals 0. That doesn't really give us anything from it. Here we get 2x minus y plus z equals 0 from the second row, and then the third row says minus 3x plus 2y equals 0. All right, so now from this equation, we can check, we can take 2y equals 3x, and so y will be 3 halves x. And then from here we get z is equal to minus 2x plus y, right? And then this will making the substitution, we will get that z is equal to minus 2x plus 3 halves y, I'm sorry, 3 halves x. After that substitution, this will be minus 4 halves plus 3 halves, so that will be negative 1 half x. Okay, so everything's in terms of x now. We can let x be 1, and then y will be 3 halves, and z will be negative 1 half. And so this you can check that this is going to be, this is in the null space of this matrix, so here's your eigenvector. And so the eigenspace, in this case E lambda, would be the span of this. So we can see that in this case the geometric multiplicity would be 1 as well, because we have just one element in our basis. For lambda equals 2, we plug that in here. We get 1 minus 2, that's negative 1, 0, 0, 2, minus 2, 1, and then negative 3, 2, and then 1 minus 2 is negative 1. All right. Once again, let's write down the corresponding equations. This will be minus x plus 0 equals 0. So we get minus x equals 0. Then we get 2x minus 2y plus z equals 0. And minus 3x plus 2y minus z equals 0. And we get a big help immediately here. We can see, because this tells us x has to be 0 no matter what. So this goes away, and so we get minus 2y plus z equals 0, which means z equals 2y. And we get the same thing here. If we let x, this term goes away, and then 2y will be equal to z. Okay. So these two things describe the elements of the null space. So once again, we can let here we can let y be anything we want, like 1, and then z is 2. So x is 0. If we let y equal 1, then z is 2. And then that's our eigenvector. And then the eigenspace will be the span of this. Okay. And once again, we see the geometric multiplicity is 1. This is one vector. And then finally, if we let lambda equals negative 1 and plug a negative 1 in here, we get 2, 0, 0, 2, 1, 1, and negative 3, 2, 2. Okay. We'll want this to be x, y, z equals 0. 2. So once again we can see that 2x equals 0, which means x equals 0 from the first row. Then we get 2x plus y plus z equals 0. So this is just 2x. 2x is already going to be 0, so we can get the x, or rather y plus z equals 0. And same thing down here, we get negative 3x, that's just 0, plus 2y plus 2z equals 0. And these equations are multiples of each other, so this last one doesn't add anything. It just says, we get z equals minus y. So once again, x equals 0, and z equals minus y. So again, letting y equal y equals 1. We get that. We get 0, 1, and negative 1 will be our eigenvector, and so the eigenspace will be the span of this. Okay, and once again, the geometric multiplicity is 2. Okay. All right. Now this is actually going to be one of the nicest cases, because we're going to see later on that these three vectors here, these three vectors that we found, they're all linearly independent, and they'll form a basis of R3, and some very nice things happen in that case. All right. So let's look at the next example. Example 2. Now this is going to be particularly nice because this is a diagonal matrix. Not diagonal, but upper triangular. Well, we said last time that we can the determinant of an upper triangular matrix can be found just by multiplying the diagonal elements. Okay, so we're not going to take the determinant of this. We want to find the determinant of a minus lambda I. So this will be 2 minus lambda 0, 0. I'm sorry, 0, 1. 0, 2 minus lambda 0, and then 0, 0, 5 minus lambda. Okay. All right. So I think we can find the determinant of a minus lambda I. Once again, you can work this out, or you can, because it's an upper triangular, just multiply all this stuff out. Or you don't multiply it out, but just multiply the diagonal elements together. Okay, and this is going to be the same thing as 2 minus lambda squared times 5 minus lambda. Okay, all right, we set that equal to 0, and we get that the eigenvalues will be 2 and 5. Okay, not surprisingly, we compare this because they're also the same here. Okay, we know that the eigenvalues are up here. All right, so we also see that in this case the algebraic multiplicity for 2 is 2, because lambda minus 2 appears twice. 2 minus lambda is just the opposite of lambda minus 2. So there you can just rewrite this as lambda minus 2 squared. It's the same thing. And then 5 minus lambda is the opposite of lambda minus 5, so the algebraic multiplicity is 1. Okay. All right. So to find the eigenspaces, if we do that lambda equals 2, and we plug this here, this will be 0, 0, 1, 0, 0, 0, 0, 0, 3. So. Okay, so that's a minus lambda I when lambda is 2, and we want to find the null space. Okay, so in this case, we see that we just get take this, we get z equals 0, the second line gives us 0 equals 0, and the third line says that 3z equals 0. Okay, so these basically say that z has to be 0. And because we don't have any information about x and y, we can just let x and y be anything we want, right? So x and y can be anything. Okay. So we're talking. So a typical eigenvector would look like, x, y, 0, which can be written as x times 1, 0, 0, and plus y, 0, 1, 0. Okay, and so these vectors are clearly linearly independent, so we can take them as a basis. So that the eigenspace is just the span of these vectors, 1, 0, 0, and 0, 1, 0. Okay. In this case, for lambda equals, and therefore the geometric multiplicity of 2 is 2. All right, when lambda equals 5. This becomes negative 3, 0, 1, 0, negative 3, 0, and 0, 0, 0. Yeah. To find the null space, we get negative 3x plus 0y plus z equals 0, then negative 3y is 0, and then 0 equals 0. So from here, y has to be 0, and z is 3x. A typical eigenvector x, y, z is going to look like x 0, 3x, or x times 1, 0, 3. And so we can see that our everything is a scalar multiple of 1, 0, 3. So our eigenspace is the span of 1, 0, 3, and the geometric multiplicity is equal to, what is it? It's 1. Okay. So once again, we'll have the algebraic multiplicity and the geometric multiplicity are going to be the same for each eigenvalue in this case. All right. One thing before we go on, we can see that now typically, okay, so like if you have an n by n matrix, the characteristic polynomial is always going to be a polynomial of degree n. And we've gotten lucky so far because we've come up with with degree 3 polynomials, and even in general there's no nice way to find the roots of a degree 3 polynomial. There's no just like we can use a quadratic formula for polynomials of degree 2, but finding a way to find the roots of a degree 3 polynomial is a lot tougher in general. However, we lucked out because these were, like in this case, this was already factored. In the other case, you could see that you could write this as x minus something times a quadratic. So this course is really about testing linear algebra. It's not about solving third degree or fourth degree equations. So the ones are going to be our examples are going to be kind of chosen to be not simple, but simpler to find the roots of the polynomial. Okay. Okay. So let's look at the next example. We have another 3 by 3 matrix. Here we have once again, we can see that this is an upper triangular matrix. We can automatically see that the eigenvalues will be 3 and negative 1. But let's just write out what a minus lambda I is. So this would be 3 minus lambda 5, 1, 0, negative 1 minus lambda 2, 0, 0, negative 1 minus lambda. And so the determinant of a minus lambda I, characteristic polynomial, will be 3 minus lambda, negative 1 minus lambda, times negative 1 minus lambda, or 3 minus lambda times negative 1 minus lambda squared. Okay. We set that equal to 0, and we get lambda has to be 3, or lambda equals negative 1. The algebraic multiplicity here is 1, because lambda minus 3 only appears once, and then for negative 1, the algebraic multiplicity is 2. Okay. All right. If we do the as we did before, let's let lambda equal 3, and plug lambda 3 in here. We get 0, 5, 1, 0 plus 2, I'm sorry, 0 minus 4, 2, and then 0, 0 minus 4. So okay. And then if we do this, this will be, I'll let you think about this for a moment if you want to pause the video, but you'll get 5y plus x is 0. Let's see. I'm sorry, try again. Z, this is a z, right? Yeah, 5y plus 1z is 0. And we also get negative 4y plus 2z equals 0. And then negative 4z equals 0. And that really helps us a lot. This last one tells us that z equals 0, and that which means that this and this is 0, which means that y has to be 0. Okay, so y and z have to be 0. There's no mention of x, so you can assume x can be anything. And so, basically an eigenvector will look like x 0, 0, or x times 1, 0, 0. So the eigenspace here is the span of just the vector 1, 0, 0. All right, now this is where the geometric multiplicity is 1 as well. Now let's see what happens for negative 1. Okay. We plug negative 1 in here. 3 minus negative 1, that's 4. So we got 4, 5, 1, 0, 4, 2, and 0, 0. I'm sorry. For negative, this is going to be 4. 4, 5, 1, then 0, 1 minus negative 1, that's negative 1 minus negative 1, that's going to be 0. And then this will be 0 as well. So what we get is 4, 5, 1, 0, 0, 2, and 0, 0, 0, 0. Okay. All right. So this we get 4x plus 5y plus 1z is equal to 0, and then we get 0 plus 0 plus 2z is 0. Okay, so that means z is 0, and this tells us that 4x plus 5y equals 0, or 5y equals negative 4x, which is y is negative 4/5 x. Okay, so x can be anything we want. Y is negative 4/5 times that, and z has to be 0. So we'll get that our vector will be, well, x, y, z then will be x, negative 4/5 x, and 0, which is x times 1, negative 4/5, 0. And so this is our eigenvector, or one of our eigenvectors. So our eigenspace is the span of 1, negative 4/5, 0. Okay, and the geometric multiplicity of this eigenvalue is 1 in this case. So this is the first case where the algebraic multiplicity and the geometric multiplicity is different, right? Because we said the algebraic multiplicity for negative 1 is equal to 2. Okay. All right. We'll talk about the significance about this a little later. Let's go to our next example. Here we have a 4x4 matrix. Okay. Okay, so let's do the same thing here. Notice I try to make this a little rather easy to compute, because otherwise things can get really, the algebra can get really messy. So a minus lambda I in this case would be 1 minus lambda 0, 0, 0, 0 minus lambda 1, 0, 0, 1 minus lambda 0, 0, 0, 0, 1 minus lambda. Okay, that's the matrix we're looking for. We can, if we take the determinant of this, looks like the easiest way is to expand out along the, well, we could either do the top row or the first column, because all three is everything, almost everything is 0. So the determinant of a minus lambda I will be 1 minus lambda times this determinant of this 3x3 matrix and probably the best way to do this is expand along the bottom row here, and so this will be 1 minus lambda times the determinant of this. This is 1 minus lambda, and it's 1 minus lambda times the determinant of minus lambda 1, 1 minus lambda, and this we can check is going to be lambda squared minus 1, which is the same thing as lambda minus 1 times lambda plus 1. So this will actually be, remember, 1 minus lambda and lambda minus 1 are opposites of each other. So, we could write this as minus lambda minus 1, and we can write this as minus lambda minus 1. The minuses cancel out, and so we get lambda minus 1 cubed times lambda plus 1. That's our characteristic polynomial. If we set that equals 0, we get lambda equals 1 and lambda equals negative 1. And the algebraic multiplicity here is 3. And the algebraic multiplicity of this is going to be 1. Okay. There's a 1 here. Okay. If we let lambda equal 1, first of all, and plug it into this matrix, we get 0, 0, 0, 0, 0, negative 1, 1, 0, 0, 1, negative 1, 0, and then 0, 0, 0, 0. Okay, and for our variables, we can just use w, x, y, z, okay, or whatever variables you want. And you get, they'll get the 4 equations. The first one will be 0 equals 0, the last one will be 0 equals 0, and then the next one will be, the second one will be negative x plus y equals 0. And then the third one says x minus y equals 0. So these basically say the same thing, that x equals y. Okay. So the other two variables can be anything we want as long as x is equal to y. So we're talking about we're talking about a vector where we have w, x, x, z, okay, which we can write as, w times 1, 0, 0, 0 plus x times 0, 1, 1, 0 plus z times 0, 0, 0, 1. Okay, and so these three vectors will be are clearly independent, linearly independent, so they will be our basis for our eigenspace. Okay, where lambda equals -1. If we plug -1 in here, we got 2, 0, 0, 0, 0 minus 2, 1, 0. I'm sorry, try again. When lambda equals -1, 2, 0, 0, 0, then 0, 1, 1, 0, 0, 1, 1, 0, and 0, 0, 0, 2. So, good. Okay. And this gives us 2w equals 0, x plus y equals 0, x plus y equals 0 again, and then 2z equals 0. So we get w has to be 0, z has to be 0, and x is minus y, or y is minus x. Okay. So, so you can see that in this case the eigenspace is going to be generated by 0, 1, -1, and 0. Okay. Right. And here the geometric multiplicity is 1 here, and I should say for when lambda is 1, the geometric multiplicity was 3. Okay. All right, so the best way to do this, again, to get good at this, practice, practice, practice. Okay, and we'll have some more theory for you in the next video. See you then.